Alright, these first four problems will be in the calculator, but we'll do a little work beforehand and then just use the calculator at the end to find the answer for most of these. Okay, so first thing, here they say let f be the function given by f of x equals 3x sine x. What's the average value of f on the closed interval from 1 to 7? Alright, right when you see this average value of f, especially when they say on an interval, so this is a tip off that you'll use that average value formula. Okay, so just in general, average value, and this is really average value of f on the interval from a to b, closed interval from a to b. Okay, so if you ever see that, so that's going to be 1 all over b minus a times the interval from a to b of just whatever that function is. Okay, so for us, the interval is 1 to 7. So we'll do 1 over 7 minus 1, which is 1/6. Integral from 1 to 7. And just that function goes inside. Alright, and that's it. And we'll just put that into the calculator. So here, let's look at the calculator now. Okay, so first to do a fraction, do alpha and the button next to it. That'll give us the 1/6. And then we'll go to math 9 for the integral. Goes from 1 to 7, and then just type in that function, and then that's going to be it. Okay, and so that's B. Let's mark these as we go. Alright, so this one, they say for question 2, for time t is greater than or equal to 0, the acceleration of an object moving in a straight line is given by a of t equals ln of 3 plus t to the 4th. What's the net change in velocity from time t equals 1 to time t equals 5? Alright, this will be all in the calculator. You know, net change is net change of a function is when you take the integral from a to b of the derivative of the function. Okay, and what this is, so this is the net change of f on the interval from a to b. Okay, so notice if we want to find the net change of a function, we're integrating its derivative. So here they want to know what's the net change in velocity from 1 to 5. That means we want to do from 1 to 5 of the derivative of velocity. Okay, but that's just acceleration, and so that's our function that we'll put in there. So this really just the integral from 1 to 5 of the acceleration function, which is just the function that they gave us. Okay, so we'll go to the calculator and then just type that in. Okay, and that's it. All right, so that's D. Okay, so there's kind of a lot to the next one, maybe. Not a lot, but um, yeah, a little math, just kind of things to know about math in general. That'll help with this problem. So here, okay, so they say, what's the area of the region in the first quadrant bounded on the left by x equals y to the fourth plus y squared, and on the right by the graph x equals 5y. Okay, so first off, oops. So let's look at this. Look at this graph first. Okay, so I graphed these in Desmos just to show you what we're gonna do. Is that crooked? Okay. So notice the red, or notice the blue are the exact graphs that they give. Okay, and they talk about they want the area in the first quadrant bounded on the left by this curve, and on the right by the line x equals 5y. Okay, so they want this area here. Okay, but notice that these are all x equals, and you can't type in x equals into the calculator. You can only do y equals. There are, I think, programs that you can do that you can run on your calculator that lets you do x equals, but for the most part you can't without those programs. But you can change all the x's to y's and y's to x's. Just switch x and y, and you get these graphs in red. Okay, so in a way, what you're doing really is graphing the inverses of these functions. But when you do that, you can, so notice like this area is what we're finding, and you can kind of tell that this area is the same thing, because when you graph an inverse, there's you get the same graph, but it's reflected over the line y equals x. So you're getting reflections of these graphs to get these graphs, and reflections don't change. They don't stretch out or compress the function. They just you get the same same shape. So these blue functions have the same shape as these red functions, and this area is going to be the same as this area. Okay, so anyways, so just seeing that what we're going to do is really find this area, and notice to find that area. So here now, let me put this back. So now we're going to focus on the red. Okay, and then for the red one, notice the linear function, in this case y equals 5x, is on top. So we're going to subtract that, or subtract this y equals x to the fourth plus x squared. We'll subtract that from y equals 5x. Okay. Okay, so the only thing really to do, so we're going to set up an integral, but we have to really know the x value here, this point here, because that's going to be what our upper limit is. We're going to go from 0 to whatever this x value is, and then we're going to integrate the top function minus the bottom function. Okay, so let's go to the calculator and first find that intersection. Okay, so I'll kind of almost always type in the functions into y1 and y2 if there's two different functions. Okay, so we'll type those in. I'll usually go to zoom 6 initially, and then I'll kind of change the window from there. So notice like it goes to -1, from -1 to about 3 in the y direction, and -1 to maybe 9 or 10 in the y direction. So we'll do that, -1 to 2 or 3 maybe, yeah, maybe 3. And then we'll go from -1 to maybe 9. Okay, so now we got a little better view of the graph. So we want to calculate that intersection point. So do second trace, which is calc. Go to 5 for intersect. And when there's only 2 lines, just move the cursor left or right till you get close to the intersection. And then just hit enter 3 times. It'll say first curve, second curve, guess. But just hit enter 3 times. Okay, so now we want this x value of this intersection point. So a little trick is if you do second quit and you go back to a blank screen. So watch this. So we'll do second quit, go back to a blank screen, and hit the store button on the bottom left. Okay, if you just get an arrow, hit clear and hit the store button again, and notice you get answer equals. And then do alpha in a letter, and so now it's going to store that letter as the x value of the intersection point. So remember this, when we calculated the intersection point, this was the x value. So here, this x value here was 1.51. So now we've got this x value. Okay. So here, so now when we set up our integral, we can set up our integral. We can see definitely it's going from 0 to this x value. But when we type in the calculator, I'm going to type in 0 to b. Okay. So that letter b is this number until you change it in your calculator. So that letter b will forever stay this number until your memory gets cleared or until you change the value of b. Okay, and then we want to do the top. So we'll do the top, in this case is the linear one, 5x. And then we'll minus the bottom function, and that minus will distribute. Oops, that should be an x. Whoops. Okay, and that's it. We'll type that in the calculator. Notice what I'm really doing is I'm doing, this is y2, and then I'm just subtracting y1. So I'm actually going to do that in the calculator. Actually, maybe I'll just type it in just like it's written. Alright, and that's it. That is answer choice A. Okay, we'll do a lot in the calculator for this one, but let's talk about what we're going to put into the calculator. So, okay, so they say the regions bounded by the graphs of y equals 4x, which is definitely this straight line. 4x is some linear function going through the origin. The regions bounded by the graph of y equals 4x and y equals x minus x squared plus x cubed are shaded in the figure. Okay, what's the sum of the areas of the shaded regions? Okay, so I'm going to show 2 ways to do it. One is kind of a standard way of doing it, I guess, and one is like a little trick that you could do in the calculator, technically by hand also, but more so in the calculator. Okay, so, to find area, we're just going to figure out the x values and then do top minus bottom, and then we'll figure out these x values and do top minus bottom. But notice on this interval here, for this shaded region, the curved line's on top and the linear function's on bottom, but from 0 to whatever this x value is, the linear functions on top and the curves on the bottom. Okay, so let's call let's say the x value of this point is a, and let's say the x value of this point is b. Okay, so what we want to do in the calculator, we want to do integral from a to 0. We can see a is some negative number. And to find this first shaded area, we'll do this top function minus this bottom function here. Okay, and okay, so we'll do the top function in this case is the curved one. It'll be x squared x cubed, and then we'll minus the 4x from that. Okay, so that'll be the area of the top one. And then whatever we get for that, or for the left one, whatever we get for that, we'll add the area from 0 to b. Okay, that's this interval from this shaded area. And then we'll do it the other way around. We'll do it the top in this case is the linear function, and then we'll have to subtract the curved function. When we subtract, remember to distribute, we're subtracting this whole function, so we have to distribute the negative, and that'll change all the signs. So it'll be a minus x plus x squared and a minus x cubed. Okay, so let's do all that in the calculator. We'll find those intersection points to get a and b, and then we'll get the area. Okay, so there's the graph. I'm going to change the window again to get this a little bit in a better view. Okay, so look at like kind of the x min and x max that'll have the areas in there that we want. Let's see if this works. -2 to 3. -6 to 10. Yeah, so that's good. So that's got our area that we're interested in there. Okay, so let's calculate these intersection points. So I'll do the left one first. Remember, just get the cursor as close as you can. Hit enter 3 times. Okay, there's our x value. So we'll second quit, go down to store. Remember, if it's just an arrow, hit clear and then hit store again. You want answer arrow. Stored as a, so that's our first intersection, x value of the intersection point. So you can just hit second trace again and intersect. You don't have to graph it first. So now we'll find the other intersection point. Hit enter 3 times. Okay, there's our x value down there, 2.3. Second quit, store that as b, different letter. And then now we can set up our integral. Okay, so now we'll do math 9. Okay, our first integral will go from a to 0, just like we have written. Okay, you can see my y equals, the linear one is y1, so you can just type in y2 minus y1 in this case. So do alpha trace and then alpha trace for the second one. Okay, that's our first area. Next one, math 9, from 0 to b. Okay, and then do alpha trace for all those functions. There's y1 there, minus alpha trace 2 for y2. That's the other area, and then now we just have to add these up. Okay, that's the answer. But let's see a better way of doing it. Okay. So another way of doing this. So there's kind of there's two nice things about a different way of doing this. So when you do it the way we just did it, first off you have to do two separate integrals, and you have to be careful with which integral is on top and which is on bottom. It's really not that big a deal if you do these separately. If you make a mistake and put the wrong function on top or bottom, then you'll get the right answer. It'll just be negative. So, you can do that and get an answer. If it's negative, just make it positive. But that's one thing. So you have to do two separate integrals, and you have to worry about which one's on top and which one's on bottom. But if you do it a different way, so we could also just do the integral from a to b, one big integral, and then just do the absolute value of the two functions subtracted. And it doesn't matter which order you do it in. Like this. So it'll just give the absolute value. It won't worry about any area if you subtract that would be negative, it'll make it positive. So here, let's see in the calculator how to do that. So do math 9, and now we can just go from a to b using that same a and b. Okay, and then do math, and then go over to the num tab. You see the absolute value is the first thing. Hit enter, and then just type in. Doesn't matter where the order. You can do y1 first, and then minus y2. And now you see we get the same answer. And just to see that you could do it the other way around, we could put I'll switch them around, put y2 first, and then subtract y1 from that, and let's see, yeah, so we get the same answer either way. Okay, so a little bit better way of doing it, a little faster, don't have to worry about certain mistakes. Yeah, so I think that's better. Okay, this next one says, they give us some graph. The graph of the continuous function f consists of 3 line segments as shown above. What's the average value of f over the interval from -2 to 8? Alright, right when you see average value of f on some interval, we know we're going to use there's really 2 ways to do it. There's average value and there's average rate of change, and sometimes those can be the same thing if your function is a rate of change function. But anyways, so we know we're going to use this formula, 1 over b minus a b of f of x dx. So this is the average value of this function, whatever this function is, on the interval from a to b. Okay, so we're going from -2 to 8. Okay, so if you do 8 minus -2, that's 10. Okay, and then to evaluate this integral from -2 to 8, we really want just this area. Okay, and then this is kind of my advice, is if you look at, if you have a triangle that's like that's inscribed in a rectangle, then the area of this triangle is going to be half the area of the rectangle. So if you look at this rectangle, this is 6 and this is 5, so that's 30, and so the area of this triangle is 15. Okay, you can also just do base times height. It's actually 1/2 base times height, which in this case isn't that much different. Okay, and then so this, we'll do 1/2 base times height for this. So this is 4 and this is 4, so 1/2, 4 times 4, 1/2 16 is 8. Okay, so this integral is really 15 plus 8, so that's 1/10 of 23, and that's just 2.3. Okay, they say for the next one, if the average value of the function f on the interval from 2 to 6 is 3, what's the value of that integral? Okay, so let's set up, according to this statement, we can get a little equation. So they say the average value of f on the interval from 2 to 6, that would be 1/4, 1 over b minus a times the integral from a to b of the function. Okay, that's the average value, and they say this equals 3. Okay, if we just actually let's leave that for now. We'll see what to do next. Okay, so next thing is, let's kind of, here we have some kind of integral from 2 to 6 of f of x. We can kind of get that in here also. We can kind of use properties of integrals to, this integral will distribute to these two things added, and then this 5 that's multiplied by f of x can be pulled out. So let's do that. First we can distribute it. Okay, and then this 5 here, we can pull out. Any constants that are multiplied can be factored out and pulled out of integrals. Okay, and then let's evaluate this right away. If you take a definite integral of a constant, you just do the constant times the difference of the limits. Okay, so notice here we have this integral from 2 to 6 of f of x, and we basically have that here. That was our original equation that we got from this statement. So notice if we just multiply both sides by 4, we'll get rid of that 1/4. So we get integral from 2 to 6 is 3 times 4, which is 12. And then now this 12 is this integral that we can use to substitute for this whole integral here. Okay, so this will just be 5 times 12 plus, and then this is just 2 times 4, which is 8. And then that's 60 plus 8, so that's 68. Okay, next they say a particle moves along the x-axis with velocity given by that function for time t is greater than or equal to 0. Okay, if the particle is at position x equals pi at time t equals 0, which of the following gives the position of the particle at the time t equals 4? Okay. So this is definitely going to be a question that's, you can think of as like final equals initial plus change. Okay, so this will be like if we want f of b function at some value. In this case we want position at 4. You can look at that function at some other value and then add the change from A to B of that function. Okay. So, and this is the way I kind of describe this. This is like the final. This is like the initial. And this is the change of that function on the interval. Okay, notice here we're given, these are just y values of the function at different x values or t values. And notice when you're doing the integral to get the change, you're using the derivative of that function. Okay, so if we want a position function, or if we want the position at some value, this is going to have to be velocity, right? Derivative of position. So that's perfect. We're given a velocity function, and we want to know something about position, so that's perfect. Okay, so let's set this up for us. So we want to know, let's say the position is x. So we want to know the position at 4. Okay, we're given the position at 0. Right, they say at t equals 0, the position is pi. So this is really pi here. And then notice this initial value goes from t equals 0, and the final value ends at 4. And so that's going to be the values of our integral from 0 to 4. Okay, notice since these are position functions, we're going to put the derivative position inside, and that's our velocity. So that's what we're going to basically type in the calculator. Okay, to get more specific, what we're really going to type in the calculator, so this x of 0, that's just pi. And then we'll do integral from 0 to 4, and we'll just type in that actual function into the calculator. Oh, I forgot this is a new calculator question, so the answer is just going to be there. I did not even look at the answer choices. Okay, so is that an answer choice just like that? Is that B? Yeah, that's answer choice B. Okay. Okay, for number 8, they say over the time interval, when t is between 0 and 10, a particle moves along the x-axis. Okay, the graph of the particle's velocity at time t is shown above. Over the interval from t between 0 and 10, the particle's displacement is 15, and the total distance traveled is 73. Okay, what's the total distance that the particle travels while moving to the left? Okay, I'm going to do it a certain way. I'm going to label all these areas. I'm going to call this area A. And I'll call this area B. And call that C. Okay, we know A and C are negative area. But we'll just, let's say A, B, and C are positive numbers. And so negative A would be the area from 0 to 2. Negative C would be the area from 7 to 10, I guess. Yeah. Okay, so displacement is it's really final position minus initial position. When you're looking at a velocity function, and looking at the graph or table or function, the area is the distance traveled. So this will be the distance it's moving to the left, since that's negative. Whatever this area is, this area here represents the distance that it travels to the right, and whatever that area is, that's the distance it travels back to the left. Okay, so displacement is really just adding these but subtracting A and C. Actually, real quick too, think about they want to know what's the total distance that the particle travels while moving to the left. So they really want to know what's A plus C. That's the distance it travels while moving to the left. Okay, so we know that b minus a minus c is 15. And then we know that, I'm going to write it this way, b plus a plus c is 73. Okay, total distance traveled is just the absolute values of all these areas. So it's just positive a plus positive b plus positive c, and that's 73. You know, this will be the distance it moves to the left, to the right, and back to the left. But the absolute value is the total distance it actually travels, and that along that path. Okay, so we want a plus c, so I think it makes the most sense to subtract these, because we can't really find a and c separately. One thing, just in general, we have 3 unknowns, but we only have 2 equations. So in math, in general, you need as many equations as you have unknowns, at least as many equations as you have unknowns. So we can't solve for these individually in this case. We could solve for b, but we wouldn't know what a and c are separately. Okay, so let's subtract these. These cancel out. And you just got to be careful. This is negative a minus a, so that's negative 2a. And then the same thing, minus 2c. And then 15 minus 73 is negative 58. Okay, and then we'll divide both sides by negative 2. Divide by negative 2. By negative 2. And then we get a plus c equals 29. And that's it. That's what we were looking for, and that's the answer. That's B. Okay, for question 9, they say the velocity of the particle moving along the x-axis is given by v of t equals e to the t minus 1 minus 1. Okay, which of the following gives the total distance traveled by the particle over the time interval from 0 to 3? Okay. So, you know, it's moving to the left and it's moving to the right, maybe, depending on if this velocity is positive or negative at certain points. We can see, let me rewrite this. Okay, we want to know when this is greater or less than 0. So let's say when it's equal to 0. Let's figure that out first. Okay, so so this is going to be 0 when this is 1, and exponentials are 1. This is an exponential function. Exponentials are 1 in general when the exponent 0. And we can see when t is 1, that makes this exponent 0. So really when t is 1, this exponent 0, which makes this 1, which makes this whole thing 0. Okay. So t is 1 is kind of the cutoff, and this is an exponential, so this increases always. So when t is bigger than 1, this will be bigger than 1. So then this will be positive. When t is less than 1, this will be negative. Okay, so 1 is the cutoff, and so here I'm going to kind of this, so 0 to 1, and then from 1 to 3. Okay, we want to, either way, we're going to be integrating this velocity function. Okay, but since this interval from 0 to 1 is an interval where this velocity is negative, we want the total distance traveled. If we integrate this, we'll get a negative position, which means it's gone to the left, but we don't want the negative part. We want just the positive part, so just negate this. That'll make that we know we're going to get a negative answer, but that'll make it positive. And then here, this velocity is positive on this interval from 1 to 3. So that'll make us like adding positions, and that's what we want anyways. So we'll just add those together. And then that is an answer choice. That is answer D. Yeah, so just figure out what, when you want to find total distance traveled up here, just figure out where the velocity is positive and negative, and then just negate negative velocities to make them positive. You can think of it that way. Okay, next one, the rate at which rain accumulates in a bucket is modeled by the function r, given by rt equals 10t minus t squared, where r of t is measured in milliliters per minute and t is measured in minutes since the rain began falling. Okay, how many milliliters of rain accumulate in the bucket from times t equals 0 to t equals 3? Okay, so first off, the rate at which, so they talk about the rate at which rain accumulates is given by this function. So this is a rate function. And then we want how many milliliters of rain accumulated in the bucket from t equals 0 to t equals 3. So we want amount of rain, but we're given a rate function of the rate that the rain accumulates. So that's perfect for integration. Okay, so we're just basically going to integrate r of t from 0 to 3. So this will be the amount of rain that accumulates from t equals 0 to t equals 3. Okay, this is kind of like a derivative function. This is a rate function. And that's what you want. You want to integrate rate functions, and those give you amounts. Usually. Okay. So let's do this. So 0 to 3. Okay, so this is like a power rule. So this is t squared over 2. When you integrate t times 10 will be 5 t squared. And then integral of t squared is t cubed over 3. Okay, so we'll plug in 3 and then plug in 0 and subtract. We can see if you plug in 0, this just equals 0, so we won't bother with that. So we'll just plug in 3. So that'll be 5 times 9 minus 27 over 3. 45 minus 9. That's 36. Okay, during a 5-kilometer road race, runners pass a viewing stand. The rate at which the runners pass the viewing stand over a certain 16-minute time interval is modeled by the continuous function r, where r is measured in runners per minute and t is measured in minutes. Okay, so r is some rate function. Okay, the graph of r is shown in the figure above. How many runners pass the viewing stand between t equals 0 and t equals 16? Okay, they want to know how many runners, but we're given a function that's runners per minute, a rate function. So the area is going to be runners. So that's what we want. We want, when they say how many runners pass the viewing stand between t equals 0 and t equals 16, they want to know how much area is under the function of the rate that runners pass the viewing stand. And so that's what we'll find up here. Okay, so we need to figure out what's all this area from 0 to 16. You can do it a bunch of different ways. I'm just going to separate it into different little figures. Okay, so this is a rectangle. This is 4 by 40. So this area is 160. Okay, this is a trapezoid. This base is 20, that y-coordinate. This base is 40, so the average is 30. And then the height is 6, so 30 times 6 is 180. What? Oh, I need to do this in different ways. So let's do that. Actually, let's do it that way. Okay. This down here is a rectangle. This is 6 by 20. That's 120. And then this is a trapezoid. These are the bases going sideways. So this base goes from 12 to 16. So this is 4. This is 6. Average is 5. And then the height is 30. 50 minus 20. So 5 times 30 is 150. And then just have to add all those up. And that'll be the amount of runners that pass the stand from 0 to 16. Okay, so those are 300, those are 310, so that's 610. This is just the integral from 0 to 16 of v of t. Okay, that's it. Okay, so this says let R be the region in the first quadrant bounded by the graphs of x equals y squared and x equals 2y. That's shown in the figure above. And they ask for what's the area. Okay, since one thing, this is the graph of x equals y squared, this curved one, and then this is the graph of x equals 2y. So they're already solved for x. This one we could have, if they were already solved for y, maybe we would just kept it in y probably. But these are already solved for x, so we'll just keep it in terms of x. Okay, and then when you want to find area, and your functions are, x equals something in terms of y, like in this case, then we're going to do right minus left. So on the right is this function. And then on the left is this function. So we're doing right minus left. Okay, and then first thing is, so we're going to do right minus left, but we have to figure out, since we're doing this, everything will be in terms of y, we'll have to figure out what's the interval that we're going to integrate over. So we really have to figure out, this is kind of the y distance. It goes from, this is the smallest y value up to whatever this biggest y value is. Okay, so we could actually set these equal to each other, these functions. Y squared equals 2y, but then you just see y equals 2 will be actually I'll do it. So to get intersection points, you set functions equal to each other. Okay, here we can technically divide by y, but then we'll have a solution y equals 0. We'll have to put that off to the side. And then divide by y, you get y equals 2. Okay, so we can see those are the two y values where they intersect. They intersect when y equals 0 and when y equals 2. Okay, and then that's kind of it. So now we'll just do integral from 0 to 2. And we'll do the right function minus the left function. Okay, let's say you did it the other way around. You did left minus right on accident. It's fine, especially for a multiple choice. You're going to get a negative answer, and then just make it positive. Realize I did it the wrong way, and so just make it positive. Okay. So now we'll take antiderivatives. Antiderivative of 2y is y squared, and antiderivative of y squared is y cubed over 3. Okay, plug in 2, you get 4 minus 8 thirds. If you plug in 0, you get 0, so we'll forget about that. And then 14 is 12 over 3. Get a common denominator. And then that's 4 over 3. That's right. Okay, and that's it. Okay, question 13. Let R be the region between the graph of y equals ln x, the x-axis, and the line x equals 5. Which of the following gives the area of the region R? Okay, so definitely going to graph this. Just a rough sketch. And really, graphing is the problem in this case. Like, is the main thing to do to figure out which answer choice it is. Okay, so just have to memorize what ln looks like. So it passes through 1, 0, and then kind of looks like root x going this way. And then technically it goes down to infinity. There's a little asymptote here. Okay, so that's ln x. And then we'll graph the line x equals 5. Let's say that's 5 there. Okay, so they say they want R be the region between the graph of ln x, this one, the x-axis, and the line x equals 5. So that's this area here. Alright, so now we can see that we want to integrate, first off, this point here is 1, 0. So we run it to find this area. We can do it. We've already got our function, this function in terms of x. So we really just want to integrate this function from 1 to 5. And that's it. So integral from 1 to 5 of ln x. Oh, okay, so I didn't look at the answer choices well enough. Okay, so they want us to do it in terms of y. Okay, so this would be the answer if they did it in terms of x, but all the answer choices are in terms of y, so we'll do it the other way. Okay. Okay, so in order to do it in terms of y, we'll really just do right minus left. So here's this function's on the right, and this function's on the left. But we have to get these both in terms of x. So first off, this is already in terms of x. This is x equals 5. But we need to get this function in terms of x. Okay, so we have our function, I'll do it up here, y equals ln x. We want to solve this for x, raise both sides to the e exponent, and then e and ln cancel, so you get x equals e to the y. Okay. So we're going to do, we know we're going to, when we do right minus left, we'll do 5 minus e to the y. So the only thing left is find these limits, but since this is in terms of y, these limits are y values. So just look at this region, the lowest y value is 0, so that'll be our bottom limit. And then the highest y value is whatever the intersection of these two functions are. And we want the y value where they intersect. So you can set these functions equal to each other and solve for y. So we'll do e to the y equals 5. Take ln of both sides. Ln of e to the y equals ln of 5. And ln and e cancel in this case. 5, so that's our upper limit. Okay, so hopefully that's an answer choice. Oh, yeah, okay, that's C. So that's the answer. Okay, the regions bounded by the graphs of y equals 6x and y equals 5x squared minus x cubed are shaded in the figure above. The graphs intersect at x equals 0, x equals 2, and x equals 3. Which of the following gives the sum of the areas of the shaded regions? Okay. So, if we're going to find the area without a calculator, without absolute value, we could do this with a calculator in one shot, use an absolute value, just one integral. But if we're going to do this by hand, we're going to have to do two different integrals, because over one interval you have a different function on top. You have this linear function on top, and then over the interval from 2 to 3, the curve function's on top. Okay, and when you want to find area, you want that positive area, you have to do top minus bottom. Okay, so we'll just do two separate integrals. Okay, this first integral goes from 0 to 2. The top function is the linear one, so that's the 6x, and then just minus the bottom function. Okay, and then just do another one from 2 to 3 that has the curve function on top. So now that'll come first. And then minus the 6x. Alright, is that an answer choice? Is that B? Yeah, that's B. Okay. That's it. Okay, so the regions bounded by the graphs of y equals 2x over pi, that's this straight line, and y equals sine x, this curve here, are shaded in the figure above. Which of the following gives the sum of the areas of the shaded regions? Okay, this is just like 14, where we'll look to see where they intersect, and those will be the intervals wherever they enter. Last question, 14, they told us where they intersect. Here we'll have to figure out where they intersect, and then those will be we'll use the x values of the intersection points to use as our limits. So let's find the x value of all these points. We know this is 0, 0. Let's find these other 2 points. Okay, so let's just set these functions equal to each other. So sine x equals 2x over pi. Okay, so this, you just have to kind of notice that when x is pi over 2 and negative pi over 2, this works. So just notice, when you set these equal to each other, just have to kind of notice if x equals negative pi over 2, so sine of negative pi over 2 is negative 1, and then if you do 2 over pi times x, which is negative pi over 2, you get negative 1 also. So if you plug in negative pi over 2 into both sides, you get negative 1, so they're equal. So that's a point. And the same thing, if x is pi over 2, sine of pi over 2 is 1, and if this x is pi over 2, the 2 and the pi's cancel to be 1 also. Okay, so it looked like they intersected at negative pi over 2 and pi over 2, and we confirmed it, so those will be part of our limits. Okay, and that's really the hard part, so now we can kind of start setting up our integral. So we know we're going to do 1 from negative pi over 2 to 0, and we'll do the top function, which is a linear one. It's 2x over pi minus sine x. Another one from 0 to pi over 2. So for this one, the sine x is on top, and x over pi is on the bottom. Okay, so we'll do the sine x first. Minus. They should have dx's with them. Alright, that should be it. Is that an answer choice? Is that C? Yeah, okay, so that's it. Okay, so for this first question from part B, it's a calculator question. They say the base of a solid is the region in the first quadrant bounded by the x and y axes, and the graph of y equals 3 minus x over x plus 1. For the solid, each cross-section perpendicular to the x-axis is a rectangle whose height is twice its width in the xy plane. Okay, what's the volume of the solid? Okay, I think first thing, it's a calculator question. Let's graph it just to see, get an idea what this graph looks like. So do alpha and the button next to it to make a fraction. Okay, and then let's graph this, see what, yeah, okay. Okay, so notice they say they want the base of a solid they say the base of a solid is the region in the first quadrant bounded by the x and y axes and this curve. So it's really this little area down here is the base of the solid that we're interested in. Okay, they say for the solid, each cross-section perpendicular to the x-axis is a rectangle whose height is twice its width. Okay, so let me draw that. This will be easy to draw. So I'm just interested in the x and y axis. And the curve looks like it does something like this. Okay, and then hits the x and y axis at a couple points there. Okay, so it's kind of easy to see these x and y intercepts. We can see, you know, the y-intercept is whatever you get in the function when you plug in 0 for x. So if you plug in 0 for x, you get 3. So this point's 0, 3. And then the x-intercept is whatever you get when you set the function equal to 0, fractions equal 0 when the top equals 0, and the top equals 0 when x is 3. So this is 3, 0. Alright, and then so they say, and we're, you know, when we're integrating these, or when we're trying to find these volumes, when they describe, you know, they describe the base of the solid, and they describe what cross sections are. We're definitely going to use this. We're just integrating this area function, and that area function is the area of a cross section. Okay, so think about this. So look at, they say first off, each cross section, which is, this is the description that we'll use to find this area function, area of a cross section. So each cross section is perpendicular to the x-axis, so cross sections are vertical. And it's a rectangle whose height is twice its width. Okay, so let's look at, like, I'm going to just pick a random height, little segment. Okay, so this is the value of the function at some x value. Call that x1. Okay, and this is the width of the rectangle, and the height is going to be twice the width. So the height is going to be something like this. Okay, and this is a rectangle here that's like coming up out of the paper. Okay, so notice this width is just really the value of the function. Whatever this value is of this function that's the width of this rectangle, and that's true for any cross section, right? If you look at like another cross section a little bit down the road, look at this cross section here, same thing. Makes another little rectangle. Okay. And this rectangle, the height is the value of the function, and then the width is the value of the function, and we know the height's going to be twice that. Okay, so let's go. So now we know we're going to go from 0 to 3, okay, because that's the bounds of this area, goes from x equals 0 to x equals 3. And if we're doing cross sections perpendicular to the x-axis, everything is going to be in terms of x. So these limits have to be in terms of x, and then our function is going to be in terms of x also. Okay, so now this width is the value of the function. So that width is just 3 minus x over x plus 1. And then we're going to multiply that by the height. And the height is twice the width. So 2 times 3 minus x over x plus 1. And that's it. So notice that, think about what we just did. We just integrated the width times the height, which is really width times height for us is area. And that's what we got, area in this case of a rectangle. All right, that's it. And so now we just got to type this in. Notice that we can just square this function, so it's like 2 times the function squared, just to make it go a little quicker. Okay. And these calculator things I pre-recorded, so just have to wait for me to do whatever I did. Imagine I'll go to blank screen first. Okay, go right to Math 9. Okay, we'll do 2, and then I'll really just get this function. That function's in y1, and just square that function. And then that'll be it. All right, that's it. That's answer choice D. Okay, next one. The base of a solid is the region in the first quadrant bounded by the graph of y equals cosine x and the x and y axes on the interval from 0 to pi over 2. For the solid, each cross section perpendicular to the x-axis is an equilateral triangle, and what's the volume of the solid? Okay, so really similar to the last one. We don't really have to graph this in the calculator first, because we know cosine goes like this. Okay, there's the pi over 2, and there's 0. Okay, so there's our cosine graph, and they say that for this volume, this area is the base, and then cross sections are perpendicular to the x-axis, so we know everything's going to be in terms of x for our integral. Okay, and then think about for this one, so if we look at like that distance right there, and we think of that as the actually let's look at like that distance there. Okay, and that's the base of an equilateral triangle. So that triangle is going to come out. Okay, hard. So it's got to be the same distance. It's going to be something like this and this, and that's going to come out of the paper. So like if you did another one, that would be a triangle, and it would come out like this, and it would just kind of keep going down the line every vertical line from the curve to the x-axis would have a different triangle, and all those triangles, those infinite triangles, would create some kind of weird looking solid. Okay, so we're going to integrate. I know we're going to integrate from 0 to pi over 2. And we're going to do, I'm going to start out thinking of it this way, just integrating area. Okay, so the area that we want is an equilateral triangle. I would memorize this formula. So the area of an equilateral triangle is s squared root 3 over 4. Okay, and so s is a side length. So we just really have to get what a side length is in terms of x. And we can see that's one of the side lengths, and they're all equal since it's equilateral. So this side length is really just the value of the function. And that's this function's cosine, so all we're really going to integrate 0 to pi over 2 of the function, which is cosine x squared. And that's it, and that'll give us our answer. Okay, so let's do that in the calculator. And I've got the function in calculator, I think. Or maybe not. Yeah, maybe not. Oh, and then just to be careful, so we'll do alpha button next to it to create a fraction. But when you're graphing cosine squared, or when you're typing in cosine squared, you do cosine x in parentheses and then square it like that. Notice the whole cosine is in parentheses and then squared on the outside. And then we'll just do root 3 over 4. And then that'll be the answer there. Okay, so that ends up being A. Okay, for question 3, they say, what's the volume of the solid generated when the region in the first quadrant bounded by the graph of y equals square root of 100 minus 4x squared, and the x and y axes is revolved around the y-axis. Okay. So let's graph this in the calculator first before we do anything. Okay, so there's the function there. Do zoom 6. Okay, so it looks almost like a semicircle, but I think it's really half of an ellipse that's centered at the origin. Okay, so notice they say this is revolved around the y-axis. So this will be this this region in the first quadrant is revolved around the y-axis. Okay, so the fact that it's revolved around the y-axis means that everything's going to have to be in terms of y. So any functions that are y equals something, we'll have to change it to x equals something. X equals something in terms of y. Okay, so let's do that first maybe. So we've got this function. Okay, we can square both sides. That gets rid of the square root on the right. Okay, and then we kind of switch things around a little bit. You can see you get 4x squared is really 100 minus y squared. And then we can divide by 4 and then square root both sides. So now we have the exact same curve, but now in terms of x, like we need it to be. Okay. Okay, so we can see this goes up to 10. You can see even when x is 0, if you plug in 0 for x, this simplifies to be 10. So we know this goes from 0 to 10. We can also tell that this will go from 0 to 5 in the x direction. That doesn't matter too much for this problem. But it will for other problems. Okay, so this is the first quadrant, and it's this area here, the area of this, that's being rotated. Good, just kind of draw, this is being rotated around the y-axis. Do a little arrow that shows that we're going around the y-axis. Alright, so technically we're doing the same as the first couple. We're integrating from a to b, some area, the area of a cross section. But these cross sections are circles, so we're doing the integral of like pi r squared from a to b. So our area function is this, our cross sections are circles, so our area function is going to be some type of pi r squared. Okay, so a radius is this distance here, and this distance is just whatever x equals, and we know x equals this function in terms of y. So now really this is our radius here for any cross section. You can see if I do a typical cross section, so this distance, first off, that's x, right? That's x, and this is a cross section of a circle. That'll look something like this. Okay, so this radius is just our function, which is x, this distance is x, but we'll get it in terms of y. Okay, so now all we're going to do is plug it in here. So now our integral goes from 0 to 10, right? You got to be careful, not 0 to 5, because these are, our function is going to be in terms of y, and actually I should have put this is really in terms of y, not x for us, in terms of y. Actually I'm going to fix that right now, because that is important. This function is going to be in terms of y, so these limits have to be y values. Just the bounds, the y values are the bounds of the function. Okay, our radius is our function. When we plug in this function and square it, this square root just goes away. So it's really just what's going to be inside here is just pi times the inside of this square root. And that's it. Okay, so the calculator, we can only type in x's, but that's fine. And 0 to 10. Okay, and I think when I pre-record these calculator things, I think I did it, yeah, oh no, I did the pi. Yeah, I did the x squared minus 100 on the top, which means there's going to be a negative 4 on the bottom. Just when I was solving it, I didn't simplify, so. Alright. That's it. Alright, so that's answer choice B. Okay, last calculator question. They say let R be the region in the first quadrant bounded by the graph of y equals 2 tan x over 5, the line y equals 5 minus x, and the y-axis. Okay, what is the volume of the solid generated when R is revolved around the line y equals 6? Okay, so we can see this. I graphed this in Desmos, so this, and we could graph it on the calculator, but just to see it when I'm explaining it. So this is the line y equals 5 minus x. You can see y-intercept is 5, and this slope would be -1. Okay, and then this is the 2 tan x over 5 function, the blue one. Okay, and then here's the y-axis. So they want us to take this area, and we're going to revolve it around the line y equals 6. Okay, so I'm going to move this over here. So let's look at the line. Let's look at kind of what we're going to do first. So here's the line y equals 6. Okay, and we're going to take this area here and revolve it over this line. Revolve it around that line. Okay, so the way you can kind of imagine when we revolve this area over this line, there's going to be whatever is here is going to be hollowed out when this area is revolved around. We'll get some kind of little bundt cake type of solid, some kind of pointy bundt cake, but the middle is going to be all hollowed out, and we'll just have this volume on the outside. Okay, the fact that we're hollowing out this volume, what that means is we're really going to find the volume when this blue, if you look at kind of the area from the blue, so we're going to take all this area from the line y equals 6 to the blue line, and we're going to revolve that around this line y equals 6. And then we're going to take all this red, this area between y equals 6 and this red line, revolve that around y equals 6, and each of those will get 2 volumes, and then we'll subtract them. So yeah, subtracting this inner volume is what's going to hollow out this, this 3D shape. Okay, so let's do that. So now first, let's set it all up first by hand, and then we'll just do it all in the calculator. So I'm going to call this x value a for now. Okay, we'll find that in the calculator later. So let's set up the integral right from the start. So we know we're going to go from 0 to a. And one thing, we're rotating it around a horizontal line. So we're rotating it around a line that's parallel to the x-axis. So that means everything's going to be in terms of x. At least if we do this washer method, which is what we're doing. Okay, if we were rotating around the y-axis or some line that's parallel to the y-axis, you know, x equals a number, everything would have to be in terms of y. Okay, but we'll have everything in terms of x. Okay, so let's do our plan. So we're really going to find the area of this, or take the area of this and rotate it around the line y equals 6. Okay, but think about when we do that. Think about a cross section to the blue. So that'll be, think about that distance. And then this will get rotated around the line y equals 6, and will be some kind of cross section like that. Okay, so we really just need this distance. Alright, this will be the radius. So when we do our pi r squared, this distance will be squared. So pi times whatever this distance squared is will be the area of this cross section. And you can see this distance is just the line is just the difference between these two functions here. So this function's y equals 6, and this function's y equals 2 tan x over 5, and so we'll subtract those. So the first one will be pi, and then that'll be, that radius is 6 minus that function 2 tan. Okay, and then we'll square it. Okay, so that'll be our first volume, but we got to hollow it out. Okay, so now we'll notice the cross section of the hollowed out, so that's going to be a radius. That'll be the inner cross section. Okay, this radius is 6 minus this function. So that's the thing that'll be squared. Start off the same. Pi times line y equals 6 minus 5 minus x. Okay, so that's the radius. We'll square that, and that'll hollow out. Okay, so that's going to be the answer. I'm just going to clean it up. So first off, both integrals are multiplied by the constant pi, so you can actually just pull that out. They're both going from 0 to a. We'll find that value of a later in the calculator. And they're really just these things subtracted inside here. And squared. And then we can just combine it all into one. Yeah, so notice I just took this thing being squared and this thing being squared, and then just put them into one subtracted because they were subtracted before. Okay, so that's the hard part. So now we just gotta type that in the calculator here. Okay, notice I made y1 the 2 tan, whatever. When you're in the test, I think it's nice to actually write that. Like, so notice, you know, here they listed the functions, so it's nice to put what the functions are, what you're using these functions as in the calculator, or what these are. So like the 2 tan, this is y1, so put y1 here, and the other one's y2, and then while you're put it into the calculator, you won't make a mistake as easily. So okay, so those are our functions. I'll change the window just to get a better view, but a lot of times it doesn't matter. Okay, yeah, so first we need to calculate that intersection, so that's going to be our upper limit of our integral. As you can, hit enter 3 times. Okay, go right back to a blank screen to store it. Done this before a bunch. Okay, so that's our upper limit, is a. So now we go right into the integral. think when I did this earlier, I forgot about pi. I think I did it as two separate ones, and I forgot about pi. So that's, remember that we want to do the first one. Doesn't really matter which one comes first, but we really want pi1 first. Squared, and then we'll do the other one, minusing the y2, the linear function. And that whole thing is squared. Okay, and I forgot the pi, but that's not a big deal. We'll just get an answer here, and then multiply it by pi at the end. Alright, so that's going to be it. That's our volume of this little hollowed out thing here. D. Okay, the base of a solid is the triangular region in the first quadrant bounded by the graph of y equals 4 minus 2x and the x and y axes. Okay, for the solid, each cross section perpendicular to the x-axis is a square. And what's the volume of the solid? Okay, a lot of times you don't have to draw a picture, but most of the time I think it's good. Okay, so come down to 2. Okay, so here's the x and y intercepts for this linear function. So the graph's going to do something like that. Or look like that. Okay, so this is the area that's the base of the solid that they describe, and they describe the cross sections perpendicular to the x-axis that are squares. Okay, so perpendicular to the x-axis, that's a cross section, and these are squares. So all those are equal. Okay, so we want to get a function that represents the area of these different squares that are coming up out of the paper, and just to see clearly, these are all squares. These are right angles. Okay, so in order to get the area of the square, we just need a side length. And we can see this is the side length that we'll really be focusing on, because this distance is really just this function. This distance is going to change with whatever x is, just like this, the value of this function changes, and they're going to be the same. Okay, so this, let's do it the certain way. So we're going to integrate. We can see we're going to do it from 0 to 2. Okay, if we want cross sections perpendicular to x, we want everything in terms of x, and this area goes from 0 to 2 in the x direction. Okay, and then every function technically that we're finding these volumes, we're integrating the area of some cross section. So for this is a square, so you could think of it as s squared dx, side length squared, and the side length is the function. So really this is 4 minus 2x squared. Okay, and then now we just have to solve this this integral. Okay, you can do it different ways. You could, probably two different ways. You could either FOIL this out and then just have few different little power rules to do. Or you can do U sub. Doesn't really matter. I'm going to do it a certain way. Oops. I'm just going to do it kind of quickly. Okay. So the reason why where I got this negative 1/6, you could do chain. You could do U sub to get this, but just know, think about if we start off with this. If we take derivative, we're going to get something like this, right? Because the 3 is going to come out. So we're going to have kind of focus on this. If we take derivative, the 3 will come out, and then you'll have a -2 that'll come out to get multiplied. So that's a -6 altogether. So this -1/6 just cancels out those constants that we'll get, because there's no constants in this. But anyways, you could just do u sub also. Okay, plug in 2. You get, you get 0. Wow, okay. So you get 0 minus. Okay, plug in 0. You get 4 cubed, which is 64. So this is -64/6. Which is positive 64/6. These two negatives make a positive, and that'll be 32/3. Okay, and that's an answer choice C. Yep, okay. Okay, next one they say, let R be the region in the first quadrant bounded by the graphs of y equals x squared. That's this curved one. And y equals 2x, this linear one, as shown in the figure above. Okay, the region R is the base of a solid. For the solid, each cross-section perpendicular to the x-axis is a square. And what's the volume of this solid? Okay. Okay, so, so they're saying if you take, if you look at kind of any distance between here, between these two curves, that distance between them will be the base of the solid, and so really that's going to be the base of each of these squares. So you have these kind of squares coming out like this, and these are all equal. And that's true any kind of distance here, that'll form a square going up. That with any little cross section. So these are all little squares. Okay, and you can imagine if you did that at every single line, it'll create some kind of strange figure. Who knows? Maybe, I don't know, like a banana sliced in half, kind of sideways. I don't know, something like that. Or something, maybe not, maybe something different. Okay. Okay, so we want to know the volume. So we really want to get, here, let's set this up. So cross sections are perpendicular to the x-axis, so everything will be in terms of x. So we know, first off, we know this goes from 0 to something. It looks like 2, and if you set these equal to each other, you get x equals 0 and x equals 2 as the solutions, and that makes sense. So those will be our limits. Okay, so we're integrating the area of these cross sections. So these are squares, so the formula is s squared. And we just now realize we just need something that represents s in terms of x. So s is like this distance between these two functions. And anytime you want to get a distance between two functions, in a vertical distance, you just subtract the two functions and that are in terms of x. So do top minus bottom. So the top is the linear function, and the bottom is this quadratic. Oops. Okay, so that represents the distance between these, but to get the area, we square it, since the area of square is s squared. Alright, and then that's maybe the hard part. Now we just have to solve that. Here we have to FOIL this out. Okay. Oops. to finish this off up here where there's room. So next thing, we'll take the integral next. So integral of x to the fourth is x to the fifth over 5. Okay, integral of negative 4 x cubed is just negative x to the fourth. And then the integral of 4x squared is 4/3 x cubed. Integrate that from 2 to 0. Okay, so we know when we plug in 0, all those terms equal 0, so we don't have to plug that in. So we just have to plug in 2. Okay, plug in 2 to the first one, 2 to the second one, and 2 to the last one. Okay, so 15 is a common denominator, so times this by 3. Okay, 16 times 15 is 240 over 15. And then multiply the top and bottom by 5, you get 160 over 15. Okay, so these are negative 400 over 15. Oh, whoops. Oh, this should be positive. That's positive, so these should be positive. I just made a mistake. Something wasn't right. Okay. Okay, so these two together are negative 80, and then that's going to be adding that. That'll be 16 over 15. Okay, and so that's answer choice A. Okay, next one. Let R be the region in the first quadrant, bounded by the graph of y equals 4 e to the x plus 2, line x equals 1, and the x and y axes. Okay, R is the base of a solid whose cross sections perpendicular to the x-axis are semicircles. So what's the volume of the solid? Okay, definitely going to draw a picture for this one. Okay, so that x equals 1. Okay. So the line x equals 1 is one of the boundaries, and then this graph, you can see like when x is 0, this is 4 plus 2, so that'll be 6. So actually we just won't make this to scale. So this will be, make this 6 here. Okay, and then whatever, it's some kind of increasing function. And this will be x equals 1. Okay, this will be y equals 4 e to the x plus 2. Alright, and so now that's what they say. First quadrant bounded by this line, and then the x and y axes. So this is the region that they're talking about. And then now they say these solids, this solid has cross sections perpendicular to the x-axis that are semicircles. Okay, so it just means, if you look here, so this will be a semicircle. So these are all semicircles. So we'll do the same thing. So first off, cross sections are perpendicular to the x-axis, so everything will be in terms of x. Our region goes from x equals 0 to x equals 1, so those will be our limits. integrate the area of a cross section. Okay, so for each cross section, the area is a semicircle. So we'll deal with the formula for the area of a semicircle. But let's get it in terms of the diameter. Okay. So if you think about it, to get the area of a full circle, you need the radius. So first off, this function, this exponential function, is the diameter at any x value. So at this little x value, this is the diameter. The value of the function is the diameter of this circle. At this x value, the diameter is the value of the function at this x value. Okay, so at every x value, this is the diameter. So here, I'll kind of do this first in terms of the diameter. Okay, so let's say d is the diameter. So to get the area of a cross section, we're going to divide the diameter by 2 to get radius. First off, we'll do pi times the radius squared, which is the diameter over 2 squared. Okay, so that's, keep in mind this is the radius, so this is really pi r squared. But that would be the area of the full circle, but we only want a semicircle, so we'll have to divide by 2. Okay, if we clean this up, divide this by 2 but square it, that'll be divided by 4, and then divide by another 2, that'll be 8. And so this, I'm going to really just pull out a pi over 8. And we'll have d squared dx. Okay, pulled out the pi, and then this 2 became this over 2 became over 4, and then over another 2. That's how we got this over 8. Okay, and then now we see this diameter is just this function. So this is pi over 8 integral, whoops. That function squared, so 4e x plus 2. Okay, so now I'm going to put this up here. Okay, so I think next thing is we'll have to square this out to get the antiderivative. Okay, so still before taking antiderivative, we'll square this first term. So 4 squared is 16, and e to the x squared is just e to the 2x. This is 16 e to the 2x. Actually, there's not much room. Let me erase this. Okay, and then we'll do 2 times that, so just squaring this binomial, and then square the last thing. Okay, now we integrate. This pi over 8, not much room. Okay, so the integral of e to the 2x is 1/2 e to the 2x, and so times 16 is 8 e to the 2x. Integral of 16 e to the x is just 16 e to the x, and integral of 4 is 4x. Okay, so I'll plug in 1 into all these, so we'll get 8e squared. We'll get plus 16e plus 4, so that's plugging in 1. And if you plug in 0, the 4x will go away when you plug in 0, but these won't. So plug in 0, this just becomes 8 plus 16, because e to the 0 is 1, e to the 0 is 1. So this will just become 8 plus 16, that'll be 24. so that's 8e squared plus 16e. Can't do anything about those, and that'll be minus 20. Okay, and then notice all the answer choices just have a pi out front. So we'll take this 1/8 and distribute it to all these, right? 8 in the bottom is really a 1/8. So basically just divide each of these by 8 to distribute the 1/8. So divide each by 8. So we have pi out front. So the 8e squared over 8 just becomes e squared. 16e over 8 is 2e. And then 20 over 8 is really 5 over 2. And that should be an answer choice. That's A. Okay, good. Okay, that's it. Okay, number 8. Let R be the region, the triangular region in the first quadrant with vertices at points 0, 0, 0, 2, and 1, 2. Okay, the region R is the base of a solid. For the solid, each cross-section perpendicular to the y-axis is an isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. Okay, what's the volume of the solid? Okay, definitely going to draw a picture. Let's do that off to the side over here. Okay, so first of all, they said it's a triangular region in the first quadrant, so we'll just draw the first quadrant. Points. So triangular version with those vertices 0, 0. There's, we'll say that's 0, 2. And then here there's 1, 2 up here. Okay, and so this is the triangular region. Okay, and that's the region R that they described, this region here. Okay, the region R is the base of the solid. For the solid, each cross-section is now perpendicular to the y-axis. So that means we're going to get this in terms of y. And it's an isosceles triangle, isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. Okay, so they're saying this one leg will be in the xy plane, the other leg will be along the y-axis, or wait, with one right angle, the right angle is on the y-axis, and then the legs in the plane. Okay, so these will kind of come out this way, kind of draw it off to the side so we can see it. Okay, so that's it. And this is isosceles, so those are equal. Okay, so that's the cross section. Okay, so everything's in terms of y because the cross sections are perpendicular to the y-axis. So the limits are going to be in terms of y. So this area goes from 0 to 2. So those will be our limits. Okay, and we're integrating an area function in terms of y. So it'll look like that. Okay, so our area is an isosceles right triangle. So it's really whatever the side length is, it's side length squared divided by 2. So it's really 1/2 s squared. Okay, so this is one of the side lengths, and this distance is whatever this function is, that's this distance, but as long as this function is x equals something in terms of y. So now we have to get what this function is. So we can see this passes through the origin, and when the slope is 2 over 1, so this line is y equals 2x, which means it's also, this line here is x equals 1/2 y. Okay, that means any distance from this function to the y-axis for this distance will be 1/2 whatever the y value is. Right, so if we're looking at like y equals 1, this distance will be 1/2. That makes sense. Okay, so now we know that this distance here is really just 1/2 y. So that's what we'll do, 1/2 y, whoops, squared dy. Okay, so let's simplify this. So when you square the 1/2, that'll be 1/4, and then we'll times it by that half. That'll be 1/8 on the outside. And then we'll just have a y squared dy at top. Okay, integral of y squared is y cubed over 3. Okay, plug in 2, you get 8 over 3. Plug in 0, you get 0, so we don't need to worry about that. And then these 8s will cancel, and just left with 1/3. That's it. Okay, next one, they say, what's the volume of the solid generated with when the region in the first quadrant, bounded by the graph of y equals x cubed, the x-axis, and the vertical line x equals 2 is revolved around the x-axis. Okay, so let's draw a picture. Okay, dealing with the first quadrant. Okay, the line y equals x cubed, at least in the first quadrant, will look kind of like that. We'll say this is x equals 2. That point there. Okay. So this whole region, so the region bounded by x cubed, line x equals 2, and the x-axis. And this is revolved around the x-axis. Okay, so put a little line there that will remind us where we're revolving around. Okay, so if we're revolving around the x-axis, then everything will be in terms of x. So we know when we set up our integral, this will be from 0 to 2. Okay, and then we're, when you, any kind of volumes of revolution, our area function is always a circle. So we're always going to be dealing with pi r squared. And we can see if we look at a radius, so like that's a radius here. And when you revolve it, this will get revolved this way. That'll be the circle that we're looking at, right? So any kind of, you can do that kind of at any point, and you'll get these little circles. And you can imagine if you did that to the full, to everything, you'll get some kind of shape, like a kind of curve, like a pyramid, but kind of that curves in. Okay, so we know we're doing a pi r squared. This is a just kind of a standard volume of revolution type problem. We're doing pi r squared, and r is just the value of this function, which is x cubed. So we're doing pi r squared dx. So our r is x cubed, x cubed squared. So that's really x to the 6th. Okay, so integral of x to the 6th is x to the 7th over 7. Okay, we don't have to worry about the 0. When you plug it in, you'll get 0, so just plug in the 2. So 2 to the 7th is 128 times 128 over 7, and then that's at 128 pi over 7. That's D. Okay, next one, what's the volume of the solid generated when the region in the first quadrant bounded by the graph of y equals x squared, the y-axis, and the horizontal line y equals 1 is revolved around the y-axis now. Okay, so revolving around the y-axis, and this is the region in the first quadrant, bounded by y equals x squared, line y equals 1, y equals x squared. Okay, so this is a region in the first quadrant bounded by x squared, y equals 1, and the x-axis, and the y-axis, sorry. Okay, so that's this region. And this is revolved around the y-axis. So we're revolving it around the y-axis here. Okay, so that means now this is the radius we're looking at. Our cross section will be some circle here. Okay, so now we know we're going to integrate definitely from 0 to 1, because this region, that's the base of this, or this region that we're revolving, in terms of y, goes from 0 to 1. Smallest y value 0, biggest is 1. Okay, and then now we need to, we know we're going to be doing a pi r squared, so pi r squared, this will be dy. So now this radius is this function here, but it's got to be in terms of y. So before we said it was y equals x squared, but now we have to fix that. So this is really x equals square root of y. So just got to take the square roots of both sides. So square root of x squared is x, pretty much, and square root of y. Okay, so that's our radius now. This radius here is root y. We'll do square root y squared. Which is really just y, as long as y is positive. Okay, integral of y is y squared over 2. Plug in 0, you get 0, so we don't have to worry about that. So just plug in 1, and you get pi over 2. And that's C. Okay, next one, they gave us a graph already, so let's see. So they say let R be the region bounded by the graph of y equals ln x, so that's this one here, horizontal line y equals 1, and the vertical line x equals 1. Okay, that's shown in the figure above. Okay, which of the following gives the volume of the solid generated when this region R is revolved around the vertical line x equals 1. So we're revolving it around this line here. Okay. So revolving it around a line that's perpendicular to the y-axis, so everything's got to be in terms of y. So our limits have to be in terms of y. So that means our limits are going to go from 0 to 1 in the y direction. I think that's the place to start. Okay, we know we're doing a revolution, so we're going to do pi r squared. And this will be in terms of y, so dy. Okay, so to get this r, this radius here, okay. So notice if it went all the way, the value, the distance from this function all the way to the y-axis is just whatever the value of this function is, right? So this function, first off, this function here is y equals ln x. Equals ln x, but if you raise both sides to the e, that means this e and ln cancel, and you get x equals e to the y. And that's the function, that's the version of the function that we'll use, because we have to get it in terms of y. Okay, so notice, the distance from this function all the way to the y-axis, this distance is e to the y. And then this distance is 1, right? This is 1 here. So it's really e to the y minus 1 gives us this distance here. Okay, and that'll be our radius. No matter what kind of radius that we're looking at, right, this will be, when we revolve it, this will be the circle that we're looking at. Oops. And this radius is the value of this function minus 1, and that gives us the radius. Okay, so the radius is e to the y minus 1. So just have to square it and dy. Okay, and nice, they don't want us to actually integrate it, so that should just be the answer there. E to the y minus 1, so that should be a. Oh no, a is not squared, so that's c. Is that right? Yeah, okay. Okay, next one, they say let R be the region enclosed by the graphs of y equals 5x minus x to the fourth, and the horizontal line y equals 3/2. Okay, the x coordinates of the points of intersections of the graph are x1 and x2, where x1 is less than x2. Which of the following gives the volume of the solid generated when R is revolved around the horizontal line y equals 3/2? Okay, let's draw this picture just roughly. Okay, so the fact that they only tell us that there's 2 intersection points, they say the x coordinates of the point of intersection are x1 and x2, so it only hits twice. And then think about it, this is an x to the fourth function, and it's a negative x to the fourth. So this will be not a parabola, but this will be some function that's goes down to negative infinity in both directions. Not a parabola, but something that might look like a parabola. But maybe around x equals 0 it does something weird, so since it's x to the fourth. So I have no idea what this function looks like. But let's say it's something like this. Let's say, who knows what it does around x equals 0. Maybe it has a couple humps, but it ultimately goes down to negative infinity. And then the line y equals 3/2 might be something like that. Shouldn't be curved, but okay. And then the region that they're talking about would be like this region here. enclosed by the two graphs. Okay, so now that's the region they're talking about. The intersection points are x1 and x2. Okay, and then now we have to revolve this around this line here. So this is all getting revolved this way. Okay. All right. So first thing, it's being revolved around a horizontal line, y equals 3/2, which is parallel to the x-axis. So everything's going to be in terms of x. So that means our limits are going to be that x1 and x2. We're doing volumes of revolution, so it's going to be pi times r squared dx. Okay, so we just have to get r. Okay, so let's take, that's a given r there. And so this would be the cross section here. Okay, this r is basically, this function, this red function, 5x minus x to the fourth, the distance from the function to the x-axis is the function itself. So we just have to subtract this little distance here, which is 3/2. So this radius is 5x minus x to the fourth, and then minus 3/2. Okay, and then we just square that, and that's it. Okay. Yeah, so that ends up being answer choice C, and that's it. Yeah, we're not squaring them separately like in B and D. That only happens when you do the washer method, and that's when there's some kind of hollowed out portion. But we can see when this gets revolved around this line, since this line is also a border, the line of revolution is a border of the area that we're revolving, there won't be any kind of hollowed out thing in the middle. And when you don't have a hollowed out thing, you don't have two separate squares that you're subtracting, usually. So, okay, so this is answer choice C. Okay, next one, they say let R be the region bounded by the graph of y equals 2x minus 2, the horizontal line y equals 2, and the vertical line x equals 1. Okay, which of the following gives the volume of the solid generated when the region R is revolved around the vertical line x equals 1? Okay, so if we're going to revolve it around a vertical line, which is parallel to the y-axis, everything's going to be in terms of y. So we know that it's not going to be C. This is in terms of x. Okay. So now let's draw a picture. So let's say the region bounded by the graph of I'll do these. So we'll do y equals 2. We'll do x equals 1. Okay, and then the graph of the actual function here, 2x minus 2. So that'll be like, so x is 0. Y is negative 2. When x is 1, y is 0. Let's go down this way. This is really what we want. Okay, so let's just make sure. So the region bounded by the graph of 2x minus 2, the horizontal line y equals 2, and the vertical line x equals 1. So it's this area is the one that's enclosed by all three of these lines. Okay, so that area is revolved around this line x equals 1. Okay. Okay, so first off, everything's going to be in terms of y. So we can see that this region goes from y equals 0 to y equals 2. So that'll be our, those will be our limits. Okay, we're doing a volume of revolution. So this will be pi r squared, and this will be dy. There's no hollowed out part, so since the border of the region is what we're revolving it around, so there's no hollowed out part. And actually, let me write this. Revolving it this way. Okay, so now this is the radius of one of these cross sections. So we just have to get this distance in terms of this function. Okay, so first off, we need to get this function in terms of x. So just add 2 and divide by 2. Okay, so this line in terms of x is x equals y. I'm going to write it as a half y minus 1. Okay, so if we look at this radius, so first off, this whole distance from here to the y-axis is this function, but we have to minus an extra 1. So it's really this function minus 1, which will be a half y minus 2. So that's our radius. Alright, and that's it. Oh, I should have left it like that. So that's really, it's really y minus, or y, oh wait, that should be plus. Oh, whoops. Oh, this should be a plus, and that should be, here, sorry, let me fix this since I didn't see those answer choices. Okay, so let's fix this. Okay, so if we solve this for x, it'll be y plus 2 over 2. And then that means this whole distance is y plus 2 over 2, so we have to subtract 1 to get this radius. Okay, so that radius that we're squaring is y plus 2 over 2, but then minus 1. Alright, so that should be it there. Okay, is that an answer choice? Yes, that's B. Okay, next one, they say let S be the region in the second quadrant, bounded by the graphs of y equals x squared ln 1 minus x cubed, and y equals negative x, as shown in the figure. Okay, so definitely this is y equals negative x, and this is that other function. Okay, the graphs intersect at x equals a, so that'll be the x value of this intersection, and x equals 0. Which of the following gives the volume of the solid generated when S is revolved around the line y equals -1? Okay. So y equals -1. Oops. Let's say is down here. And this is the line that we're revolving around. Y equals -1. I write that. Okay, so we can see if we revolve this area around this line, there's going to be some kind of hollowed out portion. All this is hollowed out. Okay, so that means we're going to do r squared minus r squared. The outer radius squared minus the inner radius squared. Okay, and all this really is kind of two volume of revolution problems in one. We're really finding two volumes, but then just subtracting the inner one to hollow out the volume. Okay, so first off, we're revolving it around a line that's horizontal, which is parallel to the x-axis, so everything will be in terms of x. So in terms of x, this goes from whatever this x value is, which they tell us is a, until 0. Sorry. Yeah, so this will go from whatever a is, whoops. Until 0. Okay, now, so we look at the outer radius, so when we revolve it, this will be on the outer, and this will be the inner. You can kind of picture when you revolve this will be on the outside, and this will be on the inside. Okay, so let's start with the outer radius. So, think about it. So this is the radius that we're dealing with. Okay. So this is, so from here to the x-axis, this distance is whatever the function is. You know, it's for different values of x's. But this will be the value of the function. And so this function is -x. So this distance is -x, whatever x is. So you can see, like, if x is, you know, -1/4, then this distance is +1/4, right? -1/4. And that looks about right. Okay, but we want the distance from here all the way down to this line, y equals -1. So this is -x, and then this is 1, so it's really -x plus 1. Okay, that's the outer radius. Let's do it like this. So outer squared minus inner radius squared. This is going to be in terms of x, and we have to have the pi. Okay, so we just figured out the outer radius is -x plus 1 squared. Okay, and then the inner radius is just this distance here. That'll be the inner radius. And we can see this distance is from this function to the x-axis, so we have to add 1 to that function. So that'll just be this function here plus 1. So all you're doing is adding 1 to these functions and squaring them. Okay. And that should be it. Let's see if that's an answer choice just like it's written. Yeah, that's D exactly. Wait, that D exactly? Yeah, okay, perfect. Okay, last one. They say let M be the region in the first quadrant, bounded by the graph of y equals 3x plus 1, the graph of y equals x plus 2, and the vertical line x equals 3. Okay, what's the volume of the solid generated when the region M is revolved around the horizontal line y equals 1? Okay, so definitely drawing this picture. So they talk about the first quadrant. Let's draw the first quadrant. Actually, let me draw this a little differently. Okay, let's make that the plus 2. Let's make that 2 actually. Okay, one of them is 3x plus 2 and the other is just x plus 2. So one of them will have a really steep and the other one will be not as steep. Okay, and then we have this line x equals 3. This is the line y equals 3x plus 2. This is the line y equals x plus 2. And this is the vertical line x equals 3. Okay. So we want the volume generated when this region, so this is the region that's bounded by all of them, and this has to be rotated around y equals 1. Y equals 1. And we're rotating it around this line. Okay, so this is another one where there's going to be a hollowed out section, right? This line of revolution, there's a gap between that and the region. So anytime there's a little gap like this between the line of revolution and the region that you're revolving around, that line, there's going to be a hollowed out section. Okay, so we're revolving it around a horizontal line, which is parallel to the x-axis. So everything's going to be in terms of x. So pretty easy to see. So this will be from 0 to 3. Okay, and we'll do outer minus inner, outer squared minus inner squared. Okay, so here, sorry, I had to kind of clip something, but hopefully this will make sense. All right, so yeah, so now we have to get the outer radius and the inner radius. Okay, so the outer radius, so technically, so this distance, let's say you look at a cross section. So we want to, one of the radiuses will be, let's say, from here down to the line of revolution. All right, so this will be one cross section. Okay, but look at this radius here, the radius of this cross section. It doesn't go all the way down. If it went all the way down, that would just be the function itself. But this doesn't go all the way down, so there's a little gap of 1 here. So we'll have to take whatever the distance is, which is the function, and then subtract 1. So instead of 3x plus 2, that'll be 3x plus 1. Okay, same idea with the other one. So this distance, if you look at this function x plus 2, the distance down to the x-axis would be x plus 2, but we have a little gap of 1, so this distance will be x plus 1. Okay, and then that's squared. Okay, so now we just have to actually evaluate this integral. Let's make sure that's right. Yeah, okay. Pi. So let's clean this up a lot. Okay, so I'm going to do this kind of quickly. So if you FOIL this, you'll get a 9x squared, and then FOIL this, you'll get an x squared, and you're subtracting. This will be an 8x squared. When you FOIL this, the middle term will be 6x. Here the middle term will be 2x. When you subtract those, you get a 4x. Okay, and then here you'll get a 1, and here you'll get a 1. When you square those out, you subtract those, just cancel out. Okay, so we'll integrate. So integral of x squared is x cubed over 3 times 8 is 8x cubed over 3. Okay, integral of x is just x squared over 2, but times by 4, 2x squared. And now we'll evaluate that from 0 to 3. Okay, don't have to plug in 0 and subtract by plugging in 0, whatever you get when you plug in 0, because that'll be a 0. So just have to plug in 3. Okay, if you plug in 3 to x cubed, that's 27, divided by 3 is 9, times 8 is 72. Okay, and then plug in 3 into here. 3 squared is 9, times 2 is 18. And then you get 90 pi. And that is answer choice B.